Last unit, differentiation took a curve and handed you its gradient. Integration runs that film backwards. Give it the gradient, and it rebuilds the original curve. It is the undo button of calculus. And here is the twist nobody warns you about. The very same backwards machine also computes exact areas under curves. So integration wears two hats at once. It reverses differentiation, and it measures area. In this final pure one unit, we turn that one idea into definite integrals, the area trapped under a curve, the area squeezed between a curve and a line, and even the volume of a solid spun out of a shape. Let's reverse the engine. Differentiating meant bring the power down and drop it by 1. To undo that, you simply run it in reverse. Raise the power by 1, then divide by the new power. That is the entire reverse power rule, and it integrates every term you will meet in Pure 1. But notice that plus C, and never forget it because examiners certainly will not. When you differentiate, any constant vanishes without a trace. So when you reverse the process, you cannot possibly know what constant was lost. Every curve with the same gradient is a candidate, stacked vertically, and plus C admits you do not know which one. Attach two limits, A and B, and the integral becomes definite, a single number instead of a family of curves. You integrate as usual, write the result in square brackets, then substitute the top limit and subtract the bottom. Best of all, the mysterious plus C cancels itself out, so you can quietly drop it. Now the magic. To find the area between a curve and the x-axis, slice it into thin vertical strips, each almost a rectangle. Add up every strip, and as the strips get thinner and more numerous, the total homes in on the exact area. That endless sum is precisely what a definite integral computes. One health warning the exam adores. If the curve dips below the x-axis, the integral counts that part as negative area. So when a region straddles the axis, split it at the crossing point and treat each piece separately, or you will hand back an answer that is too small, sometimes even 0. To find the area trapped between a curve and a line, the idea is wonderfully simple. Subtract. Integrate the top function minus the bottom function across the region where they overlap. The line carves off a slice, and top minus bottom hands you exactly the area caught in the gap, with no fuss. Finally, the grand finale. Take the region under a curve and spin it a full turn about the x-axis, and it sweeps out a three-dimensional solid, like clay on a potter's wheel. Slice that solid into thin discs, and each disc is a circle of radius y, with area pi y squared. Add up every disc from A to B, and the sum becomes an integral. The volume equals pi times the integral of y squared with respect to x. So the whole of Pure 1 integration ends where it began, with the same reverse machine, now stacking circles into a solid. Reverse, and you can measure anything. Here is the whole unit as one poster. Integration is differentiation reversed. It finds the antiderivative, the original curve a gradient came from. The reverse power rule does it in one move: raise the power by 1, divide by the new power, and tack on plus C, because differentiation destroyed whatever constant was there. That plus C is the constant of integration for any indefinite integral. Add two limits and the integral becomes definite. Integrate, bracket, substitute the top limit and subtract the bottom, and the plus C cancels, so a definite integral needs no constant. That definite integral is exactly the area under a curve between two x values. Stretch the idea, and the area between a curve and a line is just one integral minus the other, top function take away bottom. And the boundary fence so you do not over-revise. In Pure 1 you integrate powers of x and nothing fancier. Integration by substitution and by parts is Pure 3. Integrating trig functions, e to the x and 1 over x is Pure 3. Differential equations are Pure 3 too. For now, reverse the power rule, mind the limits, and this page is the whole game.